All right, we're going to finish up chapter 8 today. And again, we're talking about concentrations. And, like I said, in chemistry, molarity is the most common, but it, there's a lot of other applications. And one of them is like when you're giving out medications, oral medications, the dose has to be formed by your concentration. Okay. If you have an IV solution, doses need to be considered. Not only the concentration of the stock medication, and again, a lot of times that's going to be in percent mass, like percent sodium chloride, whatever. But you have to figure out the flow rate. Okay, you can't just bombard somebody with it, like fill it up. I don't, if you guys ever watch the vet shows, like I always watch Dr. Pol, and the cows get milk fever and they have to give them calcium. Okay, but they have to watch their flow rate, because if they give them too much calcium too fast, what will happen is the cows will go into cardiac arrest. And the same thing can happen with you. So when you're getting an IV, they have to calculate the volume and the time. That gives you the flow rate. Okay, so there's kind of standard flow rates that they give you. Again, you can't take it too fast, because then you're going to have some problems because of it. So when you're looking at medications and stuff, you're looking at the concentrations, and then there's some things you need to do to modify them. Okay. All right. One of the other things we look about when we talk about concentration, especially when we're talking about human health, is osmosis and dialysis. Okay. You guys might have family members or friends that have to go through dialysis, especially if they're diabetic and their kidneys don't work very much anymore. But one of the things they talk about is there's a selective permeable membrane between them. And what it does is it allows some things to pass and other things not to pass. Your cells have that. Your cells want certain things to stay inside, and they want things to leave, like waste products. And if they make hormones and stuff, they got to get out in the blood and go where they're supposed to go. And we need certain things to come inside, like food and, stuff like that the cell needs. So they have this membrane. Here's a cell membrane, and it's a double layer, a bilipal layer, and it allows some things to go in, some not to go in. Okay, so it's a barrier. It's like a gate. Okay, so when you have to go through dialysis, they use these membranes, and what they're doing is they're bypassing your kidneys aren't functioning. So you have a lot of stuff that needs to get out of your blood. So they basically filter your blood, and they use a membrane like this that allows the things that are supposed to get out of there, and the things that are supposed to stay in your blood, stay in your blood. Okay. So again, that membrane controls what goes in and out. All right. The most important factor usually is size. Okay. If it's too big, it's not going to go in or out. If it's small, it can whip in and out as much as it wants. Okay. So when they're doing the membranes for like dialysis, they got to make sure they're the right size. They got to make sure you take out the waste products that your kidneys aren't filtering out for you, but you don't want to take out your blood cells and all that other stuff. So there's certain things. So they have, again, factors is the size and the polarity. Okay. Because you can attract these guys, because they have charged particles, so you can use other charges to get them through. Okay. So a different concentration of ions on either side of the membrane. Okay, what will happen is they like to be the same. Okay, if you have more concentrated on this side than this side, they want to be the same, so the particles are going to move so that both sides are the same. That's like a natural thing that occurs. Okay, if you can't do that because of the membrane between them, then what ends up happening is you could end up what they call a hypertonic solution, where you have a high solute concentration. Think of hyper, somebody's hyperactive, they're super high energy. These guys have high solute concentration. Hypotonic is a low concentration. Okay, so hypertonic means it has high solute. Hypo means it has low. Hypo, low, or you can think of hypothermia, where you have low temperature or something like that. Anyway, what you really want is isotonic. Iso means the same, equal. Okay, so you want the same concentrations, and here you can see they have some electrolytes. Like inside a cell, your sodium concentration is 10. Outside the cell, like in your blood, it's 140. So you can see there's a big difference. Okay, so you've got these concentrations. So inside the cell would be hypo, outside the cell would be hyper. Same with chlorine. But now when you get to calcium, you have more calcium inside than you do in your blood, 140 versus 4. So Inside the cell would be hyper, outside the cell would be hypo. Okay, give you an idea. All right. So what does all this mean? Well, if the solid particles can't move to equal each other out, then what will happen is water will move, because water can go through those membranes. Water is really small, 2 hydrogen, 1 oxygen, really small little guy. So it can move through and it will equalize. It's a natural thing that occurs to equalize the concentration. Okay. In dialysis, what happens is the movement of these small solute through this membrane. So if you've ever seen somebody when they've had dialysis, they have to, they hook them up through their vein or whatever. And basically they take out their blood, they filter out all the bad stuff and they put it back in again. So they have a membrane to take out the stuff that shouldn't be in your blood. Okay. So the thing with solid particles, they're in constant motion and they go through a process called diffusion. And diffusion is a natural process. Okay. It happens. I mean, you don't have to do anything for it. It's just something, it's kind of like gravity. Gravity happens, diffusion happens because the solid particles are always moving. Okay. And solutions with different concentrations, they're going to have a concentration gradient. They're going to want to move those particles so that they're the same. The natural thing is to be equal. The amount of particles to be equal on each side of that membrane. Okay. And when they're not, then you have a gradient and then something has to happen. Okay. Solid particles, if they're small enough, will diffuse from hyper to hypo. They'll do that on their own if they're small particles. They'll go where there's too much to where there's too little, and then eventually they'll even out. But if they're too big, then the water has to move. Okay, so if the solid particles can't move through the membrane, then the solvent will move, and that's osmosis. So when the water moves, that's osmosis. Okay, so if you look here, before osmosis, over here we have 0.2, over here we have 0.4. So this is the hyper because it has more. This is the hypo because it's low. Okay, now this isn't natural and your body doesn't like this. So what's going to happen is, because the particles can't move across the barrier, the water will. Okay, so now the water will go over here to dilute this, and eventually they'll both be 0.3. But you can see there's a lot less liquid on this side than this side. The water had to move over in order to neutralize that. Okay, so osmosis always occurs when you have hypotonic and it'll go over to the hypertonic to dilute it. Okay, that's the natural thing that always happens. Okay, a hypertonic then, because it needs water to dilute it, it's going to increase in volume. So this side's going to have less volume. Here they started with equal volume, but because the solid particles, normally what would happen is some of these solid particles would move over here so that they were both the same. But they can't get through that barrier, so instead what they're going to do is the water's going to move, because water can always go through the barrier. And then they'll be the same. Okay? All right. So osmolarity is determined by the total concentration of the solute, not their identity. So it doesn't matter if you have what solutes you have, if it's sodium, chlorine, potassium, whatever. It matters how many you have. And if you really want to, I can show you how to determine that. That's something we do in 122 General Chem. We actually figure out the osmolality, but we don't have to do that. Okay, so osmosis can be stopped or reversed by applying external pressure. Okay, so if I go back here, if I put pressure here, I can force those guys back over. That is, when you put that pressure in there, that amount of pressure needed to stop the flow of the solvent, that's what they do in dialysis to make sure that the right things go out and the wrong things don't. Okay, so there's pressure added. And again, I can show you how to determine that if you want, but that's something we do in 122. Okay, so high pressure will force the solvent back to go back to hypertonic. That's not what it wants to do. And if you do that, then you're going to have to use energy. And if you've heard of reverse osmosis, that's what's going on. They're causing water to move against the grain. If you are one of those that buy water for your house in the big jugs, you go put your coins in and you fill your jugs and bring them home and put them in your water, what are those things called? Water towers, whatever. That water that you buy is gone through reverse osmosis. Okay, they use it to purify the water to get rid of that. And in order to do that, it takes energy. That's why you got to pay it's not too bad. I think it's like $2.40 for 5 gallons. But anyway, reverse osmosis is making the water go opposite of what it wants to. And because it has to do that, you have to use energy. Okay. Okay, if you look here, here's what happens. This is a normal red blood cell. They kind of have this little disc because this gives it more surface area. The more, remember, your red blood cells' job is to drop off oxygen and pick up waste products. Well, the more surface area they have, the better they can do that. That's why red blood cells don't even have a nucleus. The nucleus takes up too much space. All they want to do is carry stuff and drop off stuff. That's their job, okay? So that's why they have this. This gives them more surface area because you got this little extra in here in the disc. Okay, that's normal. Okay, if you have a hypotonic solution, in other words, out here, out here you have more solids, so out here is hypertonic, in here in the cell it's hypotonic. What's going to happen is they're going to want to dilute that. We're going to want water to diffuse in. I'm sorry, I said that wrong. Yeah, this is hypo out here. I said inside, sorry. So we have more particles in here than we have out here. So what's going to happen is your, normal process, we've got to make these be the same. So in order, we got to dilute this guy here. So water is going to diffuse in. And what happens if it's too much of a gradient difference, then this cell is going to, they say it lyses. It means it blows up. It explodes because there's too much water in it. Okay, so if you have a solution out here that's hypotonic, okay, that means in here we have hypertonic, which means there's more solid particles in there out here. Water is going to flow in and it's going to make this cell, if it's too much, explode. And look at it, loses that nice disc, so it doesn't, this red blood cell isn't nearly as good as it, this one is. Okay, if we have the opposite, okay, so out here we have hypertonic, so we have more particles out here than in here. What's going to happen is we're going to have water leave here. It's going to try to dilute it, and what's going to happen is the cell's going to shrivel up. This looks kind of like a space alien. Actually, it looks like a chicken head. Here's the eye, here's the beak, but the red blood cells don't have this nice shape. They don't do their job, and if they take too much water out, they shrink up to nothing. Okay, so these cases aren't good. This is what you want, isotonic, same inside and out. Okay, if you have more particles inside, water is going to go in there, kaboom. If you don't have, you have more out here, the water is going to leave, and this is going to shrink up to nothing. So that's what happens. Okay, so IV solutions they really need to be isotonic, otherwise they're going to mess with your red blood cells. Because you're putting that into your veins, it's going to go in your blood, and it's going to mess with these guys. And most of your blood, is water, and you've got a lot of plasma in there. But red blood cells, when you're looking at particles, there's more red blood cells way more than white blood cells and platelets and all these. These are the main dudes. This is the shape you want them to be, to do their job. And so if you get an IV solution and it's not isotonic, you're going to have these issues. Neither of them are good. Okay? You don't want to have goofy looking red blood cells. You don't want them to blow up, and you don't want them to shrink up to nothing. Okay? And I think we're done. Yes, we are. We are done now with chapter 8.